Here we're going to look at sections 5, 6, and 7. First one deals with ionic solids and just a few more properties of ionic solids, just kind of remind you here. Okay, ionic solids have the cations and the anions. Okay, they tend to have higher melting points and higher boiling points because they have a full element that's positive and a full element that's negative, so it's a little more holding it together there, a little more attraction. As your charge increases, okay, your melting point or boiling point increases because there's more being gained and lost there, so there's more of an attraction. Okay, valence electrons are really confined to your atoms, so the cations and the anions really have their electrons close to them, okay, the ones that are gained or lost, and so there's no movement of electrons, which means they do not conduct electricity as a solid. They're also very brittle because your positive and your positive line up. I remember we talked about this last year. If I have an ionic solid that looks something like that, and so when you hit one of these, this whole section here moves downward. So if I have this whole section here move down a little bit, okay, then my positive will be lined up with the positive and the negative lined up with the negative, and then you'd end up with like charges repel. Okay, now we'll look at section 6 with molecular solids. Remember, these are also called covalent. It's the same thing. Okay, here you're going to have everything's held together by an intermolecular force. So we're dealing with either a dipole-dipole hydrogen bond or dispersion, and that's what keeps one molecule combined to another molecule because they're actually covalently bonded, but the intermolecular force holds your molecules to another molecule. These are just an intermolecular force holding one to another and not a positive and a negative attraction in the sense of like a whole element being positive or negative, just the partial positive or partial negatives. We're dealing with a lot lower melting points and boiling points. They're usually a lot softer. They're usually less brittle than an ionic because there's usually not as much of a repeating pattern. Other than that, you have a lot of properties that really depend on what kind of intermolecular force it is, a hydrogen bond versus a dispersion or a dipole-dipole, okay? Also as well with those is that your shape or your size of the molecule is also a very large factor in what kind of properties molecular solids or covalent solids have. Okay, the last little one we're going to look at is going to be a covalent network solid and what they are. And this one's going to take us a little bit because we're also going to talk about semiconductors, okay? Covalent network solids, you're dealing with large networks of covalent bonds, okay? They have a higher melting point, they have larger intermolecular forces because they are these big networks of tons and tons of covalent bonds. We're dealing with diamond and graphite. You see all of these covalent bonds from one thing to the other. There's no intermolecular force, they're all bonded together. All of these bonds together make them much stronger, which make their melting points much higher and makes them much harder compounds. You're also dealing with diamond is one of them, like I said there in a second, okay, a second ago, and they're dealing with layers of all of these atoms. Okay, so that's kind of what they are. Now we're going to talk about semiconductors. Okay, when you deal with a semiconductor, we talked about this molecular orbital thing. We're dealing with kind of two parts of these molecular orbitals when you have Si, Ge, or Sn. And you're dealing with what we call a conduction band and what you call a valence band. Okay, the valence band, or not, it's not bond, it's a valence band, is what's formed from the bonding molecular orbitals. The conduction band is what's formed from the anti-bonding molecular orbitals. Okay, you have a semiconductor when you have the valence band that's filled with electrons and your conduction band is empty. Because I kind of mentioned this earlier when we talked about this part where we dealt with different bands for like nickel atoms. We talked about the kind of bottom bucket and the top bucket when you're dealing with filling these electrons. Well, think of the valence band as that bottom bucket, the ones that are full, and then the top band there is the conduction band, which is the anti-bonding, okay, which ones really don't want to be in. Okay, so just to kind of recap again, all right, this last little part, I don't think I said this, separated by a band gap part, okay? The valence band and the conduction band are actually separated by what they call a band gap, and that's what we're going to look at here in a second. But just, again, remember you got a semiconductor, something that usually kind of conducts, and we're explaining why it kind of conducts. You have the valence band at the bottom, which is the bonding orbitals. You have the conduction band on top, which is the anti-bonding orbitals, okay? There are different classes of semiconductors based on what the band gap is, which means how far apart these two bands are, okay? If you have an elemental semiconductor, that's only one type of atom, which is why it's called elemental. Okay, so that's one class of a semiconductor. You can also have a compound semiconductor, which is just what it sounds like. It would be a compound. So we're talking about two or more elements or atoms. Or types of atoms. And you have the elemental semiconductors all come from group 4A. When we talk about 4A, that's actually group 14. You're dealing with carbon, Si, Ge, Sn, Pb. Okay, elemental ones that come from that one. Okay, the band gap, how that goes with this now. Okay, the gap between, or the band gap for a compound. So how far apart the conduction band and the valence band are for a compound one tends to increase as your difference in group numbers increases, or as they get further apart. And we're usually talking by like groups, okay? Increasing the horizontal separation of elements leads to an even bigger difference in gap. So again, if you're going to go horizontally, which is actually this way, if you're going to go from one period to another period, so period 1 to period 4, that's a horizontal, okay, difference. That's also going to lead to a larger band gap. Okay, so will GAP have a larger or smaller band gap than ZNS? So I find zinc and sulfur. We find Ga and P. And we look at them. What's further apart from one another? Well, I have zinc in the middle of the table, and then I have sulfur over there in group 16, and then I have phosphorus and Ga. Well, Ga and phosphorus are closer together than Zn and S. So Zn and S, that's going to have your larger band gap. Because they're further apart. Okay, which means that gap between my molecular orbitals and my anti-bonding and my bonding molecular orbitals is much larger. Okay, so it's that gap we're talking about right here in the middle. What wants to bond and what really kind of doesn't want to bond, basically. Okay, well that leads us to, this whole point is dealing with what they call doping for semiconductors. Okay, you can really influence how conductive a semiconductor is by adding small numbers of an impure substance, and I call that doping. So if I have a crystal of Si, so I have a whole bunch of Si's, okay, you can replace a couple of those Si's with phosphorus, okay? Well, phosphorus, okay, if I look at phosphorus compared to Si, phosphorus here has 5 electrons. Each silicon only has 4 electrons. So if I dope in or add a little phosphorus instead of one of those Si's, you're adding an extra electron. Well, if you add that extra electron is forced to go into my conduction band, which is what makes them more conductive, because one of those extra electrons from phosphorus gets pushed up into the conduction band, and now it can conduct electricity fairly well. Those are called N-type semiconductors because your negatively charged electrons have increased, because your negative charge has gone up. Those are N-type, okay? The electrons move very easily in their conduction band. That's why it's called the conduction band, because they can move around a lot, okay? You can also go the other direction, okay, and dope a semiconductor so that there are fewer valence electrons than the original one. And we actually call those P-type semiconductors. And how that works is if you have Si again, this is what they call a host material. I want to add aluminum for one of those SIs. Okay, well, aluminum only has 3 electrons. Silicon has 4. So you now have a hole there. Okay, and that spot where you lost that electron is actually called a hole. Okay, and there's no negative anymore. Since you lost that negative, they're thought of as positive, and that's what they call p-type semiconductors. Okay, you only need a few parts per million to actually change the conductivity of a semiconductor and make it much, much, much more conductive. Okay, so now we're going to figure out which ones are which type of semiconductor. Okay, so if I have silicon to start, okay, and I want to add Ga, As, or C, and I want to yield an N-type semiconductor, which what that means is that I want to add one that has more electrons or valence electrons than Si. So I take a look at them and I say, okay, Ga has 3 valence electrons. As has 5 valence electrons. And then I go over to C. C has 4 valence electrons. So if I wanted N-type dope with Si, I would have to use As because it has 5 valence electrons. If I wanted a P-type one, I would dope that with Ga or gallium.